In order to analyze all the forces being applied on an object, we do something called free body diagram. Free body diagram basically means you free all the environmental forces around the objects that are affecting on the object movement. You isolate all the surroundings, applying a force on that object. In this case, we have the bucket and the spring. We see that the bucket is applying through his weight or gravitational force. In this case, let's say 6 Newton, and there is the force of the elasticity of the spring of the scale that is pulling the bucket upwards. So in this case, we take the bucket, we isolate it on the side, and we replace all the forces or all the things in the environment that are applying a force on the objects with an arrow. In this case, we have the elasticity of the spring of the scale can be represented as a vector pointing upwards, and we call it Fs, standing for F scale. And we have the gravity force, as we said, pulling downwards, so that's Fg. In this case, you create a free body diagram for your bucket, and you're able to analyze all the forces being applied on that bucket. If you want to follow a certain order on how to apply the free body diagram, firstly, you identify the object that you need to do a free body diagram for. In this case, we need to do the bucket. In other case, maybe it is the scale. So you need to know which object you are directing or you are looking at to be able to isolate it. You sketch the object in isolation with a dot at its center. You identify all the forces acting on the object. You ignore all the forces acting on other objects. You include in the free body diagram, and you choose the appropriate reference coordinates and include which direction is positive and which direction is negative. You can see here we had the convention upward is positive, downwards is negative, and based on that you can do your analysis as we will learn as moving forward. So you can use either the Cartesian x and y coordinates. You can use up and down, forward and backward, right and left to set your convention of signals. Then you can use as well north, south, east and west. If possible, choose an appropriate scale if you're doing any graphical analysis. Then you draw the forces proportionally extending out from the dot at the center of the object. So you can see here we draw the F gravity or the force being applied by gravity on the bucket downward from the center, and the F spring, the elasticity of the spring, is a force pointing upwards. And we set the convention and we're able to set up the free body diagram, and now we're ready to do whatever analysis we want to do on the bucket. Before we learn how to do analyses on the objects and using free body diagram in more details, let's touch base a little bit on types of forces you could face while solving problems related to free body diagram. And in many dynamic problems, free body diagram is the first step to do. Then you need to be able to identify what type of forces you're talking about here. So you have a book sitting on a table. This book has a weight, so this weight can be represented as F gravity. So the weight is being pulled downward, or the object is being pulled downward by his weight through the gravitational force, and the surface will be pushing upwards with a force called normal force. So any object at a certain surface is resisting a natural force that's called a normal force. This normal force is always applied perpendicular to the center of the object with respect to the surface. So in this case, F normal is upwards. In this case, the book is on a sliding curve with an angle of the surface. Then here the book is having the gravitational force being pulled downwards. It's not perpendicular to the surface, but the normal force is perpendicular to the surface. And of course, the book will be about to slide. It is grabbing the surface of the table, let's say in this case. So there is a friction force being applied backward. If the book is still on the surface, that means friction force is stopping it from rolling downward. There is a force as well that is called external force. That's when you apply a certain force on the object. So in this case, we have a group of forces. So we have a box sitting on the floor. There's somebody pushing this box. F up in this case is the applied force by this person. He's pulling to the right, while the friction is pulling to the left because, you know, the edge of the carton or of the object over here is scratching over the surface, and there is a roughness to the surface that will apply friction force to it, make it very hard to slide it around. And there's as well the weight of the box, which is the F gravitational, and there is the normal force that is always there, pushing against the center of the object perpendicular to the surface. Now let's take an example on how to analyze the free body diagram of a certain object. There's a car with a weight Fg of 10,000 newtons downwards. It is coasting on a level road. The car experienced a normal force of 10,000 newtons upwards, a force of air resistance, in this case 2,500 newtons backward, and force of friction exerted by the road on the tires of 500 newtons backward. Draw a free body diagram for the situation. So the car is cruising or coasting. There is no forward force acting on the car, so there is no force coming to the car from the engine. In this case, you're just only coasting, like you stop pushing the gas. There's no force into the car, it's just coasting. And the free body diagram in this case would be, you take the car, then you decide where is the center of that car, and you isolate any force around it. No surface, no air, nothing. You start to analyze the forces. Replace each environmental object affecting the car. We start with the gravitational force. That's the weight of the car pulling downwards. We have natural or normal force pulling upwards relative to the center of the car and to the surface, or perpendicular to the surface. And we have the F air pulling backwards. If the car is going to the right, then the air will be pushing the car backwards. And there is the friction as well pushing backward, because the wheels are scrubbing on the floor and the floor is trying to apply friction through the roughness of the surface. In this case, we have a convention: up and forward are positive directions, backward and down are negative directions. And you can draw a scale if you want to, 2000 newtons. I don't feel it is necessary in this case. In many cases, when you use the free body diagram abbreviated as F.B.D, you need to find the resultant force. Let's say there's an object and there is a force being applied to the left and another force being applied to the right. Forget about this angle. Then in this case, you need to find the resultant force, or the net force. Resultant force means which force would win in this fight. One force pulling left, one force pulling right. Where does the object go eventually? You need to know the resultant force to be able to tell, okay, it will go 10 newtons to the right, or -5 newtons to the left, and so on. So the net force is the vector sum of all forces acting simultaneously on an object. We will take more examples and take more details on how to find the resultant force in the coming slides.